We're going to talk about molecule shape and polarity today. So molecule shape has an effect on a lot of things, and one of the things it has an effect on is polarity, whether or not a molecule has a dipole moment. And we'll talk more about that here in a moment. So we'll start off first here talking about electronegativity. And this is just a reminder that we've talked about electronegativity before. Electronegativity is the ability an atom has to attract electrons towards it when it's bonded with another atom. We're sharing electrons, but not necessarily sharing those electrons equally. So as a reminder, the periodic trend, if we take a look at the periodic table, a rough sketch of the periodic table, as we go down the periodic table, electronegativity, this ability to attract electrons when bonded, is going to decrease down, and it's going to increase to the right. And so we can take a look at electronegativity and how it affects polarity of molecules here really quickly. So let's take a look at HF first. If we draw the Lewis structure of HF, it looks like this. We have hydrogen bonded to a single fluorine. For the sake of ease, I'm not going to draw the unshared pairs of electrons all around this fluorine. And so if we try to predict which one of these two atoms is more electronegative, hydrogen is going to be located, of course, right here on the periodic table. Fluorine is right here on the periodic table. So we would say that fluorine is the more electronegative atom, meaning fluorine is going to draw the electrons closer to it. So we will have more electrons spending time kind of, let's say, in the electron cloud closer to the fluorine, something like that. And that's what's going to happen here. Now, when that occurs, we get a couple things happening. Oops, let me erase this here real quick. And some of the things that we get happening are, if we remember, obviously electrons are negative, and so we're going to get a slightly negative charge on this side of the molecule, and we're going to get a slightly positive charge on this side of the molecule. And we illustrate that by using a little delta sign, so delta negative and delta positive. What this means is this molecule now has what is called a dipole, a partial charge on an overall neutral molecule. So we can look at both the bond and we can look at the molecule. And the bond itself, just looking at the bond, is going to be a polar bond. And polar means that you have an unequal sharing. Or it means, well, and then we'll look at the molecule rather than the bond. And we're going to say that the molecule is also polar, essentially meaning there is a non-zero dipole. Or another way to say that is there's a slight charge on this molecule, and you see the slight negative charge because all those negative electrons are being pulled towards the fluorine molecule, or fluorine atom, I should mean to say. Let's take a look at the diatomic fluorine here next. And Lewis structure, again, we're going to, for just ease, we're going to ignore all of the unshared electrons right now. And this is going to be a nice linear molecule, and we have a single covalent bond between two fluorine molecules. Now, because we have two identical atoms pulling on these electrons, there's going to be no winner for electrons. One fluorine is not going to be any stronger than another fluorine. They both have equal electronegativities. And so we're going to say that in this molecule, the bond is going to be nonpolar, because in this case, you're going to have equal sharing of the electrons around those fluorine molecules. And the molecule itself also nonpolar because there's going to be a zero dipole. Or another way to say that is there is not going to be a positive charge and a negative charge on one fluorine and the other fluorine. Let's look at an interesting case that comes with carbon dioxide now. Now, carbon dioxide, as we know, Lewis structure is going to look like this. Again, ignoring the unshared pairs of electrons on each oxygen, 2 pairs on each oxygen. Now, if we look at just, let's look at just this portion of the molecule here. We know by the positioning on the periodic table that oxygen is more electronegative than carbon. So what is going to happen? What is going to happen is oxygen is going to pull those electrons in this direction so that it has more electrons. But we also know, based on our molecular geometry, this is a 180-degree bond angle, and this is a very linear molecule. And so we're going to have an equal pull in the opposite direction from the other oxygen. So something interesting happens here. The bond between one carbon and one oxygen, we are going to say, hey, that's a polar bond. They're unequal sharing. But the overall molecule is going to be nonpolar. And the reasoning is you have equal and opposite pulls. And in physics, when we have equal and opposite pulls, they cancel each other out. Think of it in terms of a tug of war where two people are equally pulling on a rope, and the rope never moves. And that's what's really happening here. We have an equal and opposite pull, which cancels itself out. Take a look at water really quickly here. Water, we've talked about before many times, is going to form, excuse me, mistake there, is going to form, I'm going to go ahead and put the engineered pairs of electrons here. So remember, it's going to form a bent molecular geometry, 104.5 degree bond angles. Now, in this case, we draw water bent, and oxygen is the more electronegative atom. So the electrons are going to be pulled towards the oxygen in this direction, and they're not going to be pulled in equal and opposite directions. They're kind of being pulled sort of in one direction this way. So this is going to have a dipole, negative on the oxygen and positive on each of the hydrogens, which gives some really unique qualities to water, which we'll talk about later in this class. So we're going to say, for as far as the bonds between the hydrogen and oxygen go, the bonds are going to be polar, and the molecule itself also polar, having a non-zero dipole or a positive charge on it. Give you a couple more here before we set you free. We have BF3. We've talked about this guy before. Boron trifluoride. We have an less than an octet on the central boron because of those highly electronegative fluorines. And this is molecular geometry 3 and 0 with 120 degree bond angles. Now, we know the fluorines are the most electronegative. We know that they're going to be pulling, but they're all pulling in equal and opposite directions, much like that carbon dioxide. So again, the bond in this molecule is going to be polar, but the overall molecule is going to be nonpolar because, again, those equal and opposite charges, this nice symmetrical molecule, those equal and opposite charges cancel each other out. I have two more examples here to show you. We have methyl chloride. CH3Cl now is the next example. So we have central carbon, and let's draw this guy. Try to do it a little bit more 3D here. With a hydrogen coming out, we have another hydrogen coming out like this. You know, hydrogen kind of going back like that. And then we have a chlorine up here like this. Now, you probably recognize this as a tetrahedral molecule, 4 and 0, and the 104.5, or excuse me, 109.5 degree bond angles. It looks like a relatively symmetrical molecule, which is the thing we're looking for on polar molecules. They're not symmetrical, but the problem is it's not really. We have this chlorine up top here, which is going to be the most electronegative atom. So, and these hydrogens down here are doing nothing. So, well, with respect to, they're trying to pull on electrons, but they're not very good at it. So we are going to get that, that dipole up here, that negative charge up here. And so, of course, we're going to have bonds that are polar, and we're going to have a molecule that is also polar. I could ask the same question. How could we make CH3Cl a nonpolar molecule? And maybe think about it, and let's make this guy symmetrical. What if we replace this chlorine with another hydrogen? Or what if we replace the 3 hydrogens with chlorines? Now we have a nice symmetrical molecule, the same atoms all the way around. Then we're going to have now a nonpolar molecule. The next one is SF4. And now this one's a tricky one because on the surface it looks like it's going to be nice and symmetrical, but it's really not. So let's take a look at this guy real quick. Sorry, we had a bit of a bell there. So SF4s are going to look like this. We have a central sulfur. On our axial, we have fluorine, and we have a fluorine. And then on our equatorial, we're going to have a fluorine here. We're going to have a fluorine there. And then kind of going back here, we're going to have an unshared pair of electrons on our central sulfur. Okay, this gives rise to a seesaw shape. We remember our molecular geometry of 1, 2, 3, 4, and 1 for shared and unpaired electrons or bonds. And so what's going to happen here is just kind of break this guy down. So let's say on our axial going up and down, we're going to have equal and opposite poles. That's fluorine's going to pull up, fluorine's going to pull down. So that's going to cancel itself out. Then on our equatorial, we have a fluorine here, and a fluorine there. But we have an unshared pair of electrons, which gives it a non-symmetrical molecule shape. So what happens is our bonds are going to be polar, and our molecule also is going to be polar, because you're going to have a net pull somewhat in this direction on the equatorial axis of a negative charge from those two fluorines. Their bond angle is going to be compressed a little bit more of that unshared pair of electrons over there. So now, if we replaced this unshared pair of electrons, let's say with another fluorine, if that was possible, or something to that effect, then we would now have a symmetrical molecule, let's say 2 atoms on the axial up and down and 3 atoms on the equatorial, nice and symmetrical. Then we would now have, we would have a polar bonds, but possibly a nonpolar molecule. And that's the difference between polar and nonpolar. Really, we're looking for two things. We're looking for the difference in electronegativities, and we're looking for that symmetry on either the axial or equatorial axis. And when we don't have that symmetry, when there's something off or missing, when there's unshared pairs of electrons or an odd atom out or something like that, like on our methyl chloride example, that's when we see some polarity coming into play.